Hi everybody. So in this video we're going to look at proof by induction for mathematical series. And we need to begin by understanding the process for a proof by induction. There are 4 steps. The first step is called a basis. This is where we prove that the initial case where n equals 1 is true. The second step is where we make an assumption, where we say the case for n equals k is true. The third step is an inductive step, where we've shown that if the proposition is true for n equals k, then it is also true for k plus 1. And then the fourth step is where we write our conclusion. So if we look at this example, we've been asked to use proof by induction to prove that this statement is true. So if we begin with our basis, this is where we let n equals 1. And we need to show that the left-hand side is equal to the right-hand side when n equals 1. So we substitute 1 into the left-hand side. So 2 lots of 1 is 2, and then 2 plus 3 is 5. And then we substitute 1 into the right-hand side, where we've got 1 lots of 1 plus 4. 1 plus 4 is 5. So we've shown that this is true when n equals 1. Now for step 2, our assumption, this is where we say that n equals k. And we assume that the sum between r equals 1 to k of the series 2r plus 3 is equal to now replacing this n with k, and we have k lots of k plus 4. So this is our assumption. For step 3, our induction, this is where we let n equals k plus 1. And we need to show it is true for n equals k plus 1 when assumed true for n equals k. So if we write this as the sum between r equals 1 to this n, which we're saying is k plus 1, of 2r plus 3, is equal to all the terms between the first term and the kth term, plus the final term, which will be where r is k plus 1. So plus 2 lots of r plus 3. And we can write this in terms of k because we've assumed that this is true for k lots of k plus 4. So we have the first part, which is assumed true for k lots of k plus 4, plus this part. And I can expand these brackets and collect the 3. So we get 2k plus 5. Then we can expand out this bracket as well. So we get k squared plus the 4k, add the 2k, plus 5. And this will factorize to make k plus 1 multiplied by k plus 5. But now we need to show that this is the same as what we have here when n equals k plus 1. So if we replace this n with k plus 1, we do the same with this one, we add the 1 to the 4, and we get k plus 5. And this is exactly the same as what we've found. So this is our third step completed. For our fourth step, the conclusion, we need to say that this is shown true for n equals 1, and it is true for n equals k plus 1 when assumed true for n equals k. Therefore, it is proven true by induction for all values of n that are elements of the set of natural numbers. Okay? Let's try another example. So for our next example, we've been asked to prove this statement by induction for all values of n that are elements of the natural numbers. So we'll begin with our basis. This is when n equals 1. We need to show that the left-hand side is equal to the right-hand side. So we'll substitute n equals 1 to both sides. We've got 3 lots of 1 squared, which is 3. For our right-hand side, we've got a half of 1. 1 plus 1 is 2. And then 2 lots of 1 plus 1 is 3. These two will cancel, so we're left with the right-hand side equaling 3. So now for our assumption, we need to show that for n equals k, our assumption is that between r equals 1 to k, so I've replaced this one with n equals k, of 3r squared will equal 1 over 2, then we'll replace each of these with k, so we'll have k plus 1 multiplied by 2k plus 1. So this is our assumption which we're going to use in the inductive step, and this is when n equals k plus 1. So we'll have the sum between r equals 1 to n, which is now k plus 1, of the series 3r squared will equal all the terms up to k, so between 1 and k, of 3r squared, plus the final term, which is when, now we can substitute this bit in terms of k from our assumption. So this will equal 1/2 of k multiplied by k plus 1, and then 2k plus 1, plus 3 lots of k plus 1 squared. And now we need to compare this to what we've been asked to prove when n equals k plus 1. So this will become 1/2 of the n, and then for this bracket we'll have k plus 1 plus 1, so this will become k plus 2, and then for this bracket we'll have 2 lots of k plus 1 plus this one, so this becomes 2k plus 3. So our goal now is to show that this is exactly the same as what we have here. And you can see that we can factor out the k plus 1 term, and we also need to factor out this half. So this will be equal to 1/2 of k plus 1. I'll just make a note that I factored this out. Then we'll multiply this by the k term and the 2k plus 1. So that takes care of this side. And then we need a 6 because we need to multiply this by a half to get 3. And we've got one of these k plus 1s, so we'll have 1 left. So now we can simplify this bracket. So we've got 1/2 of k plus 1 multiplied by 2k squared plus k, and then 6k plus 6. We'll tidy this up. So we've got 1/2 of k plus 1, and then 2k squared plus the 7k plus 6. And you can see that we can factorize this quadratic term into 2k plus 3 and k plus 2. And this is exactly what we've been asked to show here. So for our fourth step, we need to write our conclusion. And this is, we've shown that it's true for n equals 1, and true for n equals k plus 1, when assumed true for n equals k, so therefore it is proven true by induction for all values of n that are elements of the natural numbers. Okay? Let's try one more example. Okay, so finally, we've been asked to use proof by induction to prove this statement for all values of n that are elements of a set of natural numbers. So perhaps you want to try this question yourself. You can pause the video, and when you come back, we'll go through the worked solution. Okay, so welcome back if you had a go. So for our basis, when n equals 1, we'll have the left-hand side, we'll have 1 lots of 1 plus 1, so we'll get 2. For our right-hand side, we'll have 1/3 of 2 multiplied by 3. And 1/3 of 6 is 2. So we know this is true when n equals 1. Now for our assumption, n equals k, we'll have the sum between r equals 1 to k of r lots of r plus 1. We'll assume that this is equal to 1/3 of k lots of k plus 1 multiplied by k plus 2. So all we've done is we've substituted n equals k into each of here, okay? Then for our induction, when n equals k plus 1, we're looking at the sum between the first term and the k plus 1 term of r lots of r plus 1 being equal to the sum of all the terms up to the kth term plus the final term, which is when r equals k plus 1. So we'll substitute that into here. We get r multiplied by r plus 1. And when we substitute r equals k plus 1, this becomes k plus 2. Now we can use our assumption to rewrite this in terms of k. So this will be equal to 1/3 of k times k plus 1 times k plus 2 plus the final term and k plus 2. Now if we go back to what we're looking to prove, if we let n equals k plus 1, then this becomes 1/3 of k plus 1. When we add 1 to that, we get k plus 2. When we add 2 to it, we get k plus 3. So now our goal is to rewrite this so it looks like this. We'll factor out the third and we'll factor out this k plus 1 and k plus 2. So I'll just make a note, I'm factoring out the third, the k plus 1, the k plus 2, and the k plus 1 and that as well. So we'll write the terms outside the brackets. And then we need this k, and we need a 3 here, because when you multiply that by a third, we get the 1. So now you can see we've got 1/3 of k plus 1 multiplied by k plus 2 multiplied by k plus 3. That's exactly the same as what we were asked to show here. So for our fourth step, the conclusion, we can say it is shown true for n equals 1 and true for n equals k plus 1 when assumed true for n equals k, so therefore proven true by induction for all values of n that are elements of the natural numbers. Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download a full lesson and worksheet from my website, mrmathematics.com.